Mainstream defense reports claim that Israel has fielded the world's first operational laser air defense system. In late December 2025, multiple media outlets reported that Israel's Ministry of Defense and Rafael Advanced Defense Systems formally handed over the first operational Iron Beam high-energy laser system to the Israel Defense Forces. News coverage describes Iron Beam, also known as ITON, as a ground-based laser interceptor intended to neutralize rockets, mortars, and drones at the speed of light. According to manufacturer statements and defense industry reporting, the system is based on high-power fiber lasers combined with adaptive optics to maintain a tightly focused beam on incoming aerial threats. Reported output power is in the roughly 100 kilowatt class, with future or developmental variants discussed in the 300 to 450 kilowatt range through beam combining. Effective engagement ranges are commonly cited as approximately 7 to 10 kilometers, depending on target type and environmental conditions. Media narratives emphasize the extremely low marginal cost per interception, often described as only a few dollars or even cents of electrical energy, in contrast to interceptor missiles that cost tens of thousands of dollars per shot. The claim presented is that Iron Beam is now operational and adds a low-cost laser layer to Israel's existing air defense architecture. At the heart of Israel's Iron Beam laser air defense system is a high-energy fiber laser class weapon in the 100 kilowatt range, with growth versions publicly discussed at 300 to 450 kilowatt. In clear atmosphere, roughly 60 to 80% of that power can reach a target at a distance of 5 kilometers after beam combining and atmospheric losses. That means approximately 60 to 80 kilowatt of continuous energy concentrated on a spot roughly 3 to 5 centimeters in diameter. This produces an irradiance of approximately 3 to 10 megawatts per square centimeter at the impact point, more than enough to overwhelm the thermal limits of most aerospace materials. For a drone, whose skin is typically composite or thin aluminum, melting around 660 degrees Celsius, composites degrade at approximately 300 to 500 degrees Celsius. This heat flux raises the surface above failure temperature in 1/10 to 4/10 of a second. The result is rapid burn-through, electronics failure, ignition of internal components, and immediate loss of control. For a missile, with aluminum alloys, steel sections, and thermal coatings, damage takes longer, typically 1 to 3 seconds of dwell time, but the outcome is the same. Sensors are blinded, guidance is lost, structural strength collapses, and aerodynamic breakup follows. Iron Beam does not destroy by explosion. It defeats targets through pure physics, concentrated energy, extreme heating, material failure, and loss of control. This is why it is extraordinarily effective against low-altitude, low-speed threats, such as drones and rockets, and serves as a powerful complementary layer against missile attacks when conditions are favorable. From a technical perspective, the term operational needs careful interpretation. Operational deployment does not imply universal effectiveness. The Iron Beam is meant to complement, not replace, missile interceptors. At the core of the limitation is atmospheric laser propagation. A laser weapon only damages a target if sufficient energy is delivered. Laser beams experience absorption and scattering in the atmosphere. This scattering becomes a dominant loss mechanism for high-energy lasers. This is not a minor issue, but a fundamental physical process. In fog, water droplets with sizes comparable to infrared wavelengths cause strong knee scattering. Experimental and modeling studies show that in low-visibility conditions, attenuation can reach tens to hundreds of decibels per kilometer. Under these conditions, attenuation becomes largely wavelength independent across the near-infrared band, meaning that shifting from 800 to 1500 nanometers does not significantly solve the problem. For a laser system like Iron Beam, this means that in heavy fog or dense aerosols, the majority of the emitted optical power is scattered or absorbed before reaching the target. As a result, delivered irradiance falls sharply and kill effectiveness is severely reduced, regardless of nominal laser output power. This weather dependence represents a fundamental limitation of ground-based laser air defense systems. There is no true escape from this constraint unless the laser platform is elevated above the densest atmospheric layers, such as through high-altitude platforms or stratospheric systems. So the key question remains: what happens when 200 missiles attack and only 10 laser defense systems stand in their way? Modern laser air defense systems operate with impressive precision, but they are fundamentally constrained by physics. Each laser system, typically operating in the range of 100 to 150 kilowatts, can engage only one target at a time. To destroy a missile, the laser must maintain a stable lock for approximately 3 to 5 seconds, known as dwell time. Now consider the scale of the attack shown here. With 200 incoming missiles and just 10 laser systems, the engagement quickly becomes sequential, not simultaneous. Even under ideal conditions, this configuration allows interception of only 25 to 30 missiles before the remaining targets overwhelm the defense. Range is another critical limitation. High-energy lasers are most effective within 6 to 10 kilometers, meaning engagement windows are extremely short when targets travel at high velocity. Any disruption, such as vibration, maneuvering targets, or atmospheric turbulence, reduces effectiveness further. Weather plays a decisive role. In clear conditions, partial interception is possible. In light fog or dust, laser power degrades significantly. And in dense fog, smoke, or clouds, interception effectiveness approaches zero. The conclusion is unavoidable. Laser defenses are powerful tools against small numbers of drones or rockets, but they are not designed to counter mass missile saturation attacks. This creates a critical gap. A gap that cannot be closed from the ground alone. The only viable path forward lies above the atmosphere, through airborne laser platforms, high-altitude balloons, or persistent aerial systems that extend engagement time, range, and coverage. Because when missiles arrive by the hundreds, physics does not negotiate.